We're going to be looking at how you do half equations, in particular for the reactions of permanganate, which is MnO4 negative, which is that purple stuff that we use. We've had a quick look at this in an experiment and seen that we can make it go colourless. It went green for a little bit if we changed the conditions to alkaline, and if we did it without putting any alkali, so no base and no acid with it, we saw that it made a brown precipitate. So what we're going to look at is how we write the balanced equations for these, because they're all a little bit different. The first one is one that we've done regularly. We've actually did it last year, so we should know how to do this. And we know that the colourless or pale pink ion that it makes is manganese 2+. And so we go through our normal process of balancing it. Yes, the metal itself is balanced. No, the oxygen isn't, so we put, for the 4 oxygens over here, we put 4 waters on this side. This, though, gives us hydrogen atoms, so we replace those, we balance those with 8H plus over here. So 4 times 2. And we know that we acidified it before we used it, so that means that this makes sense, that we've got H plus as a reactant. What's not balanced yet is the charge. The sum of the charges on the left-hand side is +7, 8 minus 1. And on the right-hand side, it's +2. So there's a difference of 5. So we're going to have to put 5 electrons on this side here. And that would be the half equation ready to be put with the peroxide or whatever else we reacted it with to make our full balanced equation. The second one, the third one we did, but the second one I want to balance was when we put hydroxide with it. And it went green. And so this is a new one for us this year. The green manganese species is called manganate. So it goes from permanganate to manganate. And that's MnO4 2 negative. This is actually a really, really easy one to balance, because the only difference is the charge. Everything else is balanced. So it just requires an electron to be added on this side. Now, with hydroxide, so alkaline conditions, it's not always that easy. So what I'm about to show you in the neutral conditions, where the brown precipitate was made, this process can be used if you get a more complicated one under alkaline conditions. Alright, so we're going to work our way through this harder one. The brown precipitate we now need to know is manganese 4 oxide, or manganese dioxide. So it's MnO2. So the manganese has gone from a +7 oxidation state to a +4 oxidation state. So I know there's going to be a transfer of 3 electrons. If my final thing doesn't have 3 electrons, I've made a mistake. We actually start by balancing it the same way as under acidic conditions. Alright, so that's why we start. It's not going to give us the final result, but it's how we start it. Again, manganese is balanced, 1 on each side, but oxygen is not. So because I'm out by 2 oxygen atoms, I put +2H2O over here. That gives us hydrogen ions. Now remember, this is in neutral conditions, so we won't be able to have hydrogen ions in our final result. But we're going to have 4H plus here. That balances everything apart from the charge. +3 on this side, 0 on this side, so 3 electrons. And you might remember that I said that the oxidation number changed by 3, so that's good. Problem is, that would need acidifying, but if it was acidified, it would make that. So we're in a bit of a conundrum. So instead what we're going to do is we're going to go, well, we know it was neutral conditions. No acid was added, no base was added. So we're going to try and get rid of these. And this is very similar to doing the equation stuff with Hess's law. And I hear the groans. Awesome. Okay, we're trying to get rid of these 4H pluses. We also know that water dissociates to make H plus and OH minus. So I could have H2O turning into, I know it's an equilibrium, but I'll do the arrow here, turning into 1 OH minus and 1 H plus. How many H pluses do I need to get rid of? Well, I need to get rid of 4. So I'm just going to put 4 in front of all of these. That means that they cancel each other out, because they're on both sides of the equation. And so now my new equation, I'll write in a different colour so it stands out a bit. my new equation will be this. MnO4 minus plus 4H2O plus 3 electrons goes to, I'm sorry, I've made a mistake there. I've forgotten there's water on both sides. So sorry, they're gone, and that becomes 2. So just like in Hess's law where we eliminate some things, I made a mistake there. So MnO4 minus plus 2 waters. You notice it's got the same number of hydrogens as H plus there. Okay, plus 3 electrons goes to MnO2 plus 4 hydroxides. And if I just check, this side has got a negative 4 charge, and this side with 4 hydroxides also has a negative 4 charge. So it's all balanced. So we're using the dissociation of water to get rid of these H plus ions. So if it's got 6 hydrogen ions in it, you do the equation 6 times. If it's got 1 of them, you just do it once. And as I forgot, and then suddenly noticed my error, don't forget you'll have waters on both sides, so you need to simplify that. So you don't have 4 on this side and 2 on this side. You have 0 and 2.
If you did take off all the waters, would it be in 3?
It would, yes. Yeah, so that's why I wanted to correct that. Good question. Okay, so that's the way that we used to do it. That's still how you start, even in alkaline or neutral conditions. Then you've got to get rid of those H pluses. And that includes if it makes H pluses. You still got to get rid of them. Okay. So you use that dissociation of water. Because it's an equilibrium, you can write it either way around. So it could be H plus OH minus goes to water to help balance that out.